Okay, so now what we're going to do is, now that we kind of understand what a derivative is and have worked a little bit with the limiting process in order to find the derivative, what you realize very quickly is that the limiting process and using the limits is quite a tedious process. And so what mathematicians have done is they've looked for shortcuts, things that they could basically just memorize some rules, some patterns that they saw so that they don't have to keep reinventing the wheel every single time. So now that we understand what a derivative is, now we're going to stand on the shoulders of giants and start learning the basic rules. There are pluses and minuses to this. It's basically no algebra involved. You're just going to memorize a rule, but then again, there are going to be many, many, many rules that you will need to memorize. So, it's kind of good in one way and bad in another. So this is where I would suggest that you start making some flashcards. Definitely some things that you're going to be going through, because there will be quite a few of these rules that you will need to basically memorize and be familiar with. When we are doing applications in the next chapter, you're pretty much going to have these down cold. So kind of like memorizing your trig facts. You eventually have to just know them, and you can't go on without knowing these. First thing I want to do is talk about the fact that if you ever see dy dx, that this is considered a noun. This is talking about a thing. It's talking about the derivative. So when it says find dy dx, then you are supposed to take whatever y is and find the derivative. So it's a noun. It's talking about a thing. If you ever see the d dx without anything there, and typically the way that you would see that is d with parentheses dx, this is telling you to take the derivative of whatever is inside of these parentheses. So this is kind of giving you an action for you to do. It's a verb. Find the derivative. This is the derivative, which you will find once you do this. And when you find this, then typically you could say, hey, that gives me the derivative, the noun. You do it, and it gives you the actual derivative. All right, so what we're going to do is we're going to start building our kind of a repertoire of rules that we're going to have. I would suggest that you kind of have a piece of paper as well as this set of notes, because what I'm going to do is I'm going to give you the derivation of several of these as we go. There's not going to be enough space here, and this set of notes kind of just gave you the rule. But then on your own paper, we will kind of go through and talk about the derivation of these things. All right, so the first one, we're going to start with kind of like with the parent graph, start with the easiest one out there. We're going to talk about the constant function. The constant function, of course, is your y equal to c, which is nothing more than a horizontal line. And it should not surprise you that our derivative of a horizontal line of a constant is going to be 0, because what is the slope at any point on a horizontal line? 0. Okay. Let's come over here on our little derivation page. So this is our proofs for your derivative rules. Kind of showing you how the limiting process works on this. And then from this point on, we'll kind of go ahead and say, hey, then we're going to memorize it. But we do want to make sure we understand how it comes about. All right? So first thing, let's do our little recall from the last section, that the derivative function for y equals f of x is given by, we're going to use the limiting process, and we can use different notations. We can call it dy dx, or we can call it f prime of x, and that in order to find this derivative, what we're going to do is the limiting process as h goes to 0 of f of x plus h minus f of x all over h. So I'm going to use the generic limit on the slope of the secant line, the difference quotient findings. All right, so first one we're going to look at is the constant function. So our constant function, when we take a look at that, is our y equals f of x is going to be a constant. So it could equal 5, 0, -2, pi, e, any kind of constant that we want. Okay? And as we saw on the previous page, its derivative is 0. And let's kind of show our proof for that. Alright, so our derivative of y with respect to x can be found by taking the limit as h goes to 0 of my f of x plus h minus f of x all over h, which in this case is kind of a very simple proof because when we're looking at it, f of x plus h, well, since it's a constant function, it doesn't matter what I plug in for x, the answer is always a y value of c. So we end up with c is the y value for x plus h, but c is also the y value for x, and we end up with the limit as h goes to 0 of 0 over h, and 0 over a number is 0. The limit as h goes to 0 of 0, limit of a constant is the constant, and we are done with our proof for that one. So that's a fairly straightforward, simple little proof, plus common sense should also kind of play into this, in that the slope of a horizontal line, any horizontal line that we take a look at, its slope is 0 at any point. Okay, so that's fairly straightforward. Right? So if we come back to our handout and you see things like this, and you say, okay, what is the derivative of the following function? And we'll use good notation here. We no longer have to do the actual limiting process. I just remember the derivative of a constant is 0. Now don't get confused. The limit of a constant is the constant. The derivative of a constant is 0. So dy dx in this problem would be 0. Even if the function is equal to 0, f prime of x is equal to 0. Over here, s prime of t is equal to 0. And then here, what you want to not get tricked by, especially when we start getting into some later rules, k is a constant, pi is a constant, squaring a constant is a constant. This is just a number. It's just a fancy looking number. So the derivative of y with respect to x is going to simply be 0. The derivative of a constant is 0. Rule number 1. Then we get to rule number 2. When we have power functions, okay, something in the form a times x to the n. Now, the rule says that what you're going to do is you're going to take your power and you're going to multiply it times your coefficient, and then you're going to subtract 1 from the power. So you multiply times the coefficient and then subtract 1. That's our rule. Okay? Now let's come over here. Let's do our derivation for this. So now we're on to number 2, and we're going to derive the power rule. Alright, we're going to start simple on this one. This one's going to take a few steps to derive. We're going to start with, alright, so we're going to say f of x. Let's start without the coefficient. We'll just say x to some power n. Right? Then our derivative, which we're going to prove, that we end up with n times x to the n minus 1. Right? So let's start with n equal to 1. Sometimes we like to kind of work our way up. So that would be y equal to x. Now, that's nothing more than a line, so that's the easiest of these to visualize. It is a line with a slope of 1 everywhere you go. So this would be fairly straightforward. And if you think about this, you'll see that our little rule is going to work. But let's go ahead and do our limiting process and show the proof. So f prime of x is going to be the limit as h goes to 0 of my f of x plus h minus f of x all over h, which will give me the limit as h goes to 0, plug in your x plus h, so we get x plus h minus your function x all over h, which will give us the limit as h goes to 0 of h over h, which equals the limit as h goes to 0 of 1. Limit of a constant is the constant. Okay? So now how does that work in the little rule that I gave you? That if I take f of x equal to x to the first, then the derivative would be 1 times well, basically 1, because the coefficient was 1 here. So we take the power times 1, x to the 1 minus 0. Oops, sorry, back myself up. 1 minus 1. Multiply, subtract 1. That's going to give me 1x to the 0, which is 1 times 1, or 1. Okay? So you can see that the rule is working, and then we have the shortcut. Okay? So now what we want to do is let's kind of make ourselves a little bit more complicated. Let's go to n equal to 2. Okay? So now we have f of x equals x squared. So the derivative, using our limit definition, we would have our limit as h goes to 0, f of x plus h minus f of x all over h, which would be our limit as h goes to 0 of x plus h squared minus f of x all over h. We do the FOILing process, x squared plus 2xh plus h squared minus x squared all over h. Don't forget your limit. You have some things that will cancel. Gone, gone. Factor out your h. So I have h, 2x plus h over h. Remove the division by 0 problem, as we've seen before. This is going to be the limit as h goes to 0 of 2x plus h, which I can now do my direct substitution. 2x plus 0, or 2x. And then again, just to verify our rule, when we had f of x equal to x squared, again this will be a 1 there, so the derivative, according to my shortcut rule, is take 2 times 1, x to the 2 minus 1, or 2x to the first, which is 2x. Okay? So we verified that it works in the case of x squared. Okay? We're going to do x cubed, and then we're going to kind of start doing a little more generic little property that's there. Okay? So now let's do n equal to 3, just to kind of verify to ourselves. So we're doing f of x equal to x cubed. So my derivative, I'm going to jump right in, limit as h goes to 0 of x plus h cubed minus x cubed over h. Now this might remind you of something, or maybe you haven't seen this before. This is called Pascal's triangle. Pascal's triangle will give you the coefficients of taking two things raised to a certain power. All I'm doing here is adding each of the previous ones, 1, 4, 6, 4, 1, and you can keep going, 10, 10, 5, 1, etc. And then what this basically is giving you is the coefficients. If I have x plus h to the 0, I get 1. If I have x plus h to the first, I get 1x plus 1h. If I have x plus h squared, I get 1x plus 2xh plus 1h squared. It's just like you're at school. You get to hear the announcements too. So it's giving me the coefficients of multiplying it out. So then, of course, this would be the coefficients of multiplying out x plus h cubed. I'm going to have a 1x cubed. Let's go ahead and write it over here since I'm at that. So the limit as h goes to 0, I'm going to have 1x cubed plus, and then we have a 3, and now we decrease the power on x by 1, and then add h to the first. And we have our coefficient of a 3, decrease the x power by 1, add 1 to the h power, and then 1h cubed minus x cubed all over h. We have the same cancellation we saw before. Everything that's left has an h in it, so we can factor it out. we can remove the division by zero problem, cancel out your h's. Then we're going to do our limit as h goes to 0, and we basically have our 3x squared plus 3xh plus h squared. We can now substitute because we removed the division by zero problem. 3x squared plus 3x times 0 plus 0 squared is 3x squared. And then again, just to verify that our derivative works, our shortcut rule, if I have x cubed, then my derivative, and again, think of this as a 1, I would do 3 times 1, x to the 3 minus 1, which is 3x squared, which is obviously way faster than what we're doing there. Okay? So this idea is that if we would keep up this process, I'm just going to kind of go dot, dot, dot. Okay? Now, there's a lot more to this, kind of looking at it. Let's do one, let's kind of take it all the way to this x to the n. Now, notice there's an actual pattern to this as we are taking a look at it. And there's a way to get these little coefficients here. These are actually combinations. If you remember from your Algebra 2 class, where we would have been doing combinations. And basically what you're going to do is you're going to do your power, what row you're on, and then your k is going to be what position you are. So, like, if the idea is when we do combinations, this would be a combination of sorry, I had to make sure I was explaining the Pascal's triangle correctly. This row coming down this way, this would be the k equals 0 row. This would be k equals 1, k equals 2, going diagonally down through here. Okay? So think of it as like position 0, 1, 2, 3, 4, 5, and so on. So that's kind of how the k is going to work. And another way of writing Pascal's triangle, I'll do this on the next page, so we would do it with a combination. So we had 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So if I do a combination of 0, choose 0, okay, where this is the power and this is the position. All right? So the position is going to be the actually I have that backwards. You know, that's what I was thinking of. I was trying not to do when I was doing this. The first number is your power. The second number is your position. Okay? So the power is going to be the n, and then the position we're going to call k, just to give it. So if you do a combination, you can pick it up on your calculator if you'll remember where this is. Let's open up my calculator really quick. So under the math menu, so if I'm going to quit to the home screen, under your math menu, under probability, NCR is a choice, so I'm going to choose that. And the power was 0, and my position was in the 0th column or diagonal coming across. And notice I get an answer of 1. And keeping that in mind, in the next row, we would have C of the power is 1, but you're in the 0 position, and then C, power is 1, and you're in the first position. Then you come down to the next row. It would be C, your power is 2, but you're in the 0 position. Then your power is 2, you're in the first position. Your power is 2, you're in the second position. And so that's kind of these combinations. You can check them on your calculator. This would be C of 3, choose 0, C of 3, choose 1, C of 3, choose 2, C of 3, choose 3, and so on and so on. So as long as you know kind of your position in the pattern, you can figure out what your actual kind of rule is. And then if you don't remember this from Algebra 2, if I have n choose k, the actual formula for that would be n factorial, what your calculator is actually doing. Remember n factorial, n times n minus 1 times n minus 2 etc. If I had 5 factorial, that would be 5 times 4 times 3 times 2 times 1, and so on. And then, so our actual formula that your calculator is using to calculate, you don't really need to know this other than just reminding you what it is. This is your combination factorial, okay? And so what that's going to do is, if I don't necessarily know the number, I can go ahead and write these in a combination form instead of writing them by going down 600 rows and then figuring out what I'm going to have, right? So here's going to be my proof for n equal to, because obviously we've got to go all the way up to, we want to go all the way up to n. So we want to have f of x equal to x to the n. So using our limit definition, our derivative would be the limit as h goes to 0 of my f of x plus h to the n minus x to the n all over h. Now what we know, of course, is since n, we don't really know it, we're going to kind of expand this out, but we're going to use the combinations. And so the first coefficient would be a combination of n choose 0, and then of course we would have x to the n. The next one would be a combination of n choose 1, and then it would be x to the n minus 1 times h. Okay. Then we would have, do one more, and then we're going to kind of do some dot, dot, dot. And we have n choose 2, x to the n, subtract another 1, because you've got to decrease by 1 again, and then h squared. And we would continue in this fashion. Now I'm going to kind of do a little pigeon math here, because I'm going to fit all this in. And when we eventually get to the other side, after we do this dot, 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 the very last one would be n choose n, and you would have x to the n minus n times h to the n. And of course, that's all over h. You kind of imagine that's all on one line there. I should have planned ahead as I was doing this. So now what's going to happen is when you start kind of looking at this is that there's kind of some patterns that we're going to see in this. And the patterns that we're going to see is that pretty much you know that and what have I forgotten? Minus x to the n. We know that this first one is always a 1, right? So this and this are always going to cancel out. Okay? Then from what we have left, we can pull the h out, because there will be an h in every single one of these. So we would do the limit as h goes to 0 of the combination n choose 1, x to the n minus 1, and I'm going to pull the h out. I'll write it in front, so I won't need an h in that one. The next one would be your combination n choose 2, x to the n minus 2, and I took one of the h's away, plus dot, dot, dot. And then here we would have our last one would be our n choose n. Now this is x to the 0, right? X to the 0, so that's going to go away, and we simply would have h to the n minus 1. Right? Because I took one of them away, and that's all over h. Now what that does is that's going to allow us to cancel this out. And what's kind of important to us as we take a look at this, kind of when I get to this stage right here, is what I'm taking the limit as h goes to 0 of. Here's this first one, x to the n minus 1, that has no h in it. But every term that comes after that, as complicated as it is, dot, 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 everything that comes after it, all of the stuff here at the end, has an h in it. So what's going to happen when I do my direct substitution is you're basically going to end up with the limit, or if we take the limit, by doing the substitution putting in h, this is going to go to 0, this is going to, because all of these have h times in it, it's going to go to 0. So you're going to end up with the combination of n choose 1, x to the n minus 1. Now, applying my formula for my n choose 1, your n choose 1 is going to be your, using my factorial formula to kind of show you this, the n factorial over my 1 factorial, which is really just 1, and then n minus 1 factorial, x to the n minus 1. Now, n factorial is really n times n minus 1 times n minus 2 times dot 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 all the way down until I get to times 3 times 2 times 1. Notice that, well, 1 factorial is 1. This n minus 1 factorial is n minus 1 times n minus 2 dot 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 3 times 2 times 1, and that's times x to the n minus 1. Notice what happens. These will all cancel out because they're in the top and the bottom, and the only thing you're left with is your n times x to the n minus 1. And so that kind of gives us our power rule, which all you really have to do is take your power, multiply it times the front, and subtract 1, and that gives us our shortcut rule. All right, so let's come back over to our differentiation rules, see it in practice. It was a big, long proof for it, but really the thing to remember is, hey, I want to take the derivative. I have a power, coefficient in front doesn't bother me, my derivative is going to be 3 times 2, x to the 3 minus 1, 6x squared. Done. Over here, I might need to use a little creative writing. This is what we call simplify early and often. I'm going to rewrite this first as 1/3 x to the 1/3, so I can write it as a power function. And then I'm simply going to apply my power rule. This would be 1/3 times 1/3 x to the 1/3 minus 1. Then we simply do a little arithmetic. 1/9 x 1/3 minus 1, negative 2/3. Now at some point you may be asked to rewrite this in a nicer form, so we may come in here and say, hey, this is the same as 1/9 cube root of x squared. So we should be able to work with that's just knowing your definition of rational exponents and negative exponents. But pretty much we have our derivative following the rule, and it's a lot shorter than the limit definition. I'm going to do the same thing here, simplify early, simplify often. This is 5/3 x to the negative pi. So notice I'm rewriting everything so that it's of the form f of x equal to ax to some power. Okay, it doesn't matter that that's not a nice number. We just need to get it in the correct form, so then I can apply my rule. The derivative of y with respect to x is going to be you multiply, and let's kind of skip this step. You can do this in your head. So you have 5/3 times negative pi, so negative 5 pi over 3 x to the negative pi minus 1. And it doesn't really matter if that's ugly looking. We've followed the rule. We have the derivative. Okay? Our last example over here, if I rewrite this in a nicer form, this would be 6x to the negative 3/5. Get it in the right form. So if I want to take the derivative, let's do y prime this time, you would multiply 6 times, I'll go ahead and write it since it's got a fraction in it, just in case y'all get a little confused, 3/5 minus 1. So I have 6, nothing cancels, so this would be negative 18/5 x to the, and you got to think of this as 5 over 5, negative 3 minus 5, negative 8/5. And then again, if you want to rewrite that into a quote-unquote more traditional form, you would have a negative 18 on the top, a 5 on the bottom, and then we have the 5th root of x to the 8th on the bottom. So that just kind of shows you the derivative of the power rule. Anytime you have a power function, we can very, very quickly take its derivative, and it's obviously way shorter than using the limit definition for that.